Welcome to the second expert webinar organized by the Stockholm Environment Institute. I'm Arno Rosemarin. Beside me is Nelson Ekane. We're both at Stockholm. We've been contracted by the Bill and Melinda Gates Foundation to discuss the Reinvent the Toilet Challenge projects, some of the grants. And these are being discussed electronically on the Sustainable Sanitation Discussion Forum. These projects are innovative and new and interesting, and they're really worth discussing, and we want to make sure that there's discussion within the community of sanitation experts as well as outside of that. So our intention with these seminars, these webinars, is really to initiate this contact and exchange between the grantees with similar projects. Some of this stuff is already on the website, as you can see on the bottom left, the Susanna.org website, and also on the discussion forum. So, hand it over to you, Nelson.
Thank you, Arno. The theme of our discussion today is innovation in toilet design and waste treatment technologies. With us today are experts from different parts of the world, from India to USA to Canada, working with interesting and innovative projects. We have Aaron Stokes from Duke University in North Carolina, USA. We have Tove Lassen from EWAC, the Swiss Federal Institute of Aquatic Science and Technology, in Zurich, Switzerland, also based in Copenhagen, Denmark. We have Vinci Baby from Aram Scientific Solutions in Kerala, India. And we have Yu-Ling Cheng from Sanitation Now, Toronto. We are glad to also have Roshan Chestra from the Bill and Melinda Gates Foundation in the USA, in Seattle. With me here is Kim, who's part of Kim Anderson, who's part of the team. Kim?
A little bit off camera.
A bit off, yeah.
And we also will be having Dorothee Spulla of Ekane in Switzerland. She will be joining us shortly. And also part of this team is Elizabeth von Munch, Ostella Consulting. She is not here today.
Okay. So each of the experts, and we have 4 experts, as you can see, will be given 5 minutes to describe his or her project. And there will be PowerPoints that you'll be able to see, and we'll be displaying and controlling them from our side.
Okay, our first speaker today is Aaron Stokes from Duke University. Aaron is a graduate student working on the project Effective Sewage Sanitation with Low Carbon Dioxide Footprint. He is developing a self-contained and energy-neutral system consisting of 2 parts, namely anaerobic digestion and heat sterilization. The system produces biogas that is used to heat sterilize the treated effluent. This is being tested in Kenya with assistance from Chep Koilel University in Eldoret. Aaron, the floor is yours.
All right, thank you. So again, I'm Aaron Stokes. I'm representing our research group at Duke University that's led by Mark DeZeus, as well as our research group that we're collaborating with in Eldoret, Kenya. The name of the university actually has recently changed to the University of Eldoret. So if we can go to the next slide. This is the conceptual framework of our project. So you can see in the middle we have a digester. It's an anaerobic digester with a floating dome so that the volume stays constant, as well as the pressure of the volume of the slurry that remains constant. And the top of the dome moves up and down with gas volume. Directly connected to that is the toilet. If all the waste from the toilet flows directly into the digester, we're operating this at high strengths of just urine and feces and possibly a little bit of flush water, a liter or less of flush. After the liquid comes into the digester and is decomposed there, the liquid will then flow into our heating system, and that's on the right side. So first it goes to the heat exchanger. It's a tube and shell heat exchanger. Then goes into the heating tank, where we operate the heating tank at 65 to 75 degrees Celsius. The heating tank is powered by burning the biogas we produce in the digester. So it's a self-sustaining process of decomposing waste and then treating that waste. So what comes out after the final pass the heat exchanger is an effluent that we hope has no pathogens. We also hope to produce extra biogas that you can use for cooking or lighting or any other energy needs that the home or community has. The system has no moving parts. It's all gravity flow, so it's very simple. And we hope to have very, very little maintenance for the system. Next. So the objectives for our project, we started off with wanting to prove the concept. We did over a year of operation in our lab here at Duke. We wanted to see if the digester could operate well under the high strengths conditions of just urine and feces, and make sure that our heating system would remove pathogens. We did test for pathogens with E. coli and used simulant urine and feces for the digester. So since March, we've had very steady conditions and are pleased with our process. So we have moved into the pilot study phase of the project. We started building in Kenya in May. We're working in Eldoret, Kenya, and working with the University of Eldoret there. We built 3 systems, each one serving approximately 25 people. And that project's ongoing, and we'll continue monitoring digester operation as well as the heating system like we did in our lab at Duke. And so for the future, we want to assess any strengths and weaknesses of the project that we can improve on and continue to use, and see about feasibility for scale-up. Also associate some cost-benefit analysis. The extra biogas has a pretty significant value in the community in Kenya. Burning fuels are very expensive. And the final effluent is high in nitrogen, which makes it a very valuable fertilizer, which is pretty expensive for the local residents. We also, in future studies, want to monitor some health impacts from our system. So next slide. Here's some lab results from what we've done at Duke. The main takeaways from this is that we are now operating at steady conditions within our digester. You can see on the left side you have digester operation, and since day 225, very stable. And since then, we have some more results, and it's continued staying in that range. But the main takeaway is we expect about 400 liters of biogas per day for a system that was designed for 10 people. On the right side, using that same system design, here's some results from our heating. And operating our heating tank at temperatures greater than 65 Celsius, we had 100% E. coli inactivation. And to operate the heating tank at this level, we needed about 230 to 280 liters of biogas per day. So we found that we will have, or we expect to have, excess biogas from the digester. Next slide. So this is some pictures from our pilot study in Kenya. On the left side, you can see the full system. Above is the latrines. And then below, we have enclosed our digester and heating system just for security and safety. The latrines need to be elevated so that everything would operate by gravity flow. On the right side, you can see what's going on below the latrines. You can see the half of the digester on the right, and it's partially submerged. And then in between the digester and the green tank you see is our heating system. The long tank is the heat exchanger, and what's behind that is the heating tank. So after everything flows to the heating system, it goes into the collection barrel where residents can come and collect the treated waste and use it as a fertilizer. And so that's what I have to present today.
Fantastic.
Yeah, thank you very much, Aaron. Very interesting project. Just a question before I give the floor to other experts to ask, and Arno. Regarding pathogen inactivation, have you tried other pathogens, other microorganisms apart from E. coli?
We haven't tested for other pathogens in the lab yet, but with those temperatures and the time in the tank, and based off of what we've seen in literature, we do expect to have an activation of, we've looked up for Ascaris and as well as coleophages. So we would expect to have an activation of those as well. But that's something that we do want to test in the future.
Okay, thank you.
Yeah, I think with the 65 degrees, you will be pretty well eliminating most of those pathogens. Welcome, Dorothy. I had a little question about the three systems for 25 persons per system. Is that one toilet, or is it several toilets for each system?
So each toilet or each system is what you saw in that final picture with the 3 latrines above connected to the digester system below.
This one.
So this left picture, we built 3 of those, and we put the way the residences are set up in this community are you have a kind of an 1/8 of an acre plot with about 25 residents on each, and so we built this system on that plot, and so all the residents of that plot share that one system. So there are 3 different plots where we built these.
Just one other question. You know, water content is so important in biogas production. And I'm just wondering how you managed to regulate that.
In the lab, we haven't regulated per se. The only thing coming into the digester is our simulant urine and simulant feces. And based on what we'd expect is about 1 liter per person per day of urine and then 400 grams of feces per day per person. And so that's all that has come into the digester. We did do a phased up loading period where we did have a higher concentration of water versus feces and urine. But once we got to about day 75, we stopped doing that and have been operating at only urine and feces coming in.
Any questions from the group that's connected? Okay, I guess we'll.
Aaron,
Sorry?
I was going to ask Aaron, how fast is the digestion?
The one in the lab we designed for a 40-day retention time. The systems in the field, the retention times are a little different, and it's also a little difficult to know exactly on some of them because some of the plots have residents that come in and out. So, you know, on average, there's 25 residents per plot, and kind of at a normal time, about 25 residents, and the retention time there is 45, 50 days. The digesters that we installed in the field are 2 cubic meters.
Okay, thank you, Aaron, for that. I think we'll move very quickly now over to Tove Larsson, and Tove will move this PowerPoint here. We have just a little descriptor on our script here. Tove is the principal investigator of this diversion for safe sanitation project. It's developing a dry source separation toilet with on-site ultrafiltration water recovery. And her team collaborates with EOOS, designing company in Austria, and Makerere University in Uganda. Is that right that it's Austria? It's not Switzerland, right?
It's Austria. It's Austria.
Okay, thanks. Good. So we'll give you the floor here for 5 minutes.
Yeah. Thank you, both of you. I'll present the blue diversion toilet developed by EOOC and EOS in Switzerland. Next, please. We chose to develop a shared toilet for 2 families and recover the resources at a larger scale for about 175 families. The toilet is a urine diverting dry toilet And because we have this change of scale, we need a logistic concept for transporting dry feces and undiluted urine to the resource recovery plants. From the urine, fertilizer is recovered at the expense of energy generated from feces. In this presentation, I'll concentrate on the toilet. Next, please. Next, please. Slide.
Yeah, sorry.
It's a urine diverting dry toilet as we know them, but in order to increase hygiene and comfort, this toilet can be flushed, and urine and the flush water is not mixed, it's separated by a technical device which the user cannot see. The water can also be used for hand washing, and it can be used for anal cleansing. It's recovered on site. Next, please. In the water wall of the toilet, it's an ultrafiltration treatment tank, but it functions exclusively by gravity. It's based on the gravity-driven membrane filtration, which has been developed at EAWAG for drinking water production. The polluted water is pumped up with a foot pump by the user, and the ultrafiltration membrane is kept open by higher organisms grazing on the membrane, so one doesn't have to maintain it. Next, please. The water comes out safe from the ultrafiltration membrane. It's without bacteria, it's without virus, but as you see, the water is slightly soiled, slightly colored, and we remove this color with electrolysis and at the same time remove the traces of organic matter and produce chlorine for disinfection. Next, please. The toilet was designed by Harald Gründel and his collaborators at EOS, but very early in the process we went to Uganda, to Kampala, and talked to the people there who are potential users whether they like the design language. Next slide. They like that, and they also like the convenience, the water tap, etc., especially the washers like the hand shower, and they like the flush button. Next, please. The maintenance interface is very important in order to secure that the people collecting the urine and feces twice a week will not be sick. So this toilet can only be opened if you pull this rim. Next, please. When you pull the rim, the feces container is sealed automatically, and the urine can be pumped with, from the bottom of this container. Next, please. You see the container can be removed also by the people themselves if, for instance, the collecting service is breaking down. Next, please. We tested this very early in the process in spring 2013 in a cooperation with Makerere University, and the field site was in Uganda. The main results were that people liked the toilet, but of course there are a lot of details which need improvement. You see it from this picture. It's difficult for the kids to reach the soap, etc. You also see that the pan looks slightly different from what you have seen until now. People open the feces lid with the foot, and afterwards when they use the shower or when they flush, this lid will close automatically and only the front part will be flushed. The advantage is that the toilet can be used for washers and wipers alike. Next, please. The business model is set up as a toilet model because nobody will be able to buy these toilets. You also see they can be placed in any superstructure you will find. Next, please. We set up a business case for Uganda in order to see whether it's realistic that this can actually be done for 5 cents per person and day as required. Obviously, this is a challenge, but because we divert urine and feces, we actually think that it's possible. We have some income from selling the nutrients, the fertilizer, and it's important that there's also a profit for the entrepreneur who will run this business, else nothing will happen. You also may see that our operational cost is relatively high. We think that it's necessary that we have funding for local maintenance. Last, please. Or next, please. There is a lot of more information on our homepage. That's all from my side.
Okay. Thank you very much, Tove. I think that was very clear. I did have one little technical question about the membrane that you're using for filtering this reused water. Is that a very expensive unit, and what is it made out of?
Yeah, these are the normal polymeric membranes which you would also use for drinking water production in a normal drinking water plant in Europe. They used to be expensive. The prices have been falling a lot in the last time. We think that about 20 to 25% of the cost of this toilet, of the construction cost, will be for the membrane, but it will last for 10 years. The important thing is that we do not have to maintain it. It will not have to be cleaned. It's included, of course, in our business case.
Yeah, just a question there, Tove. Regarding, you said people like it. How many people are we talking about?
Well, 400 people were using the toilet. Some of them only once, and 3 families were using it for each 2 weeks. There were about 1,500 people being interviewed, and also interviewed about their willingness to pay, which was quite high, higher as it, or about as high as it needed to be. Of course, the problem is that people have very little money, but that's not anything which we can do anything about. There will be a social science report on this investigation. EAWAG financed an additional social science study. So our social scientists, they are looking into also all these interviews which they made and all these responses which they got.
Any questions? Yes,
Larson? Yeah, hello, Larson. I have one small social, I have one social, question. I don't know how people feel, how they say that they like it, because normally what I notice from the people in the such slum communities or informal settlement or poor settlement, when you bring the advanced technology like this, sometimes they may be hesitate to use that, and most often they may hesitate to use that because it is too advanced for them, and and then I don't know how. Number one, of course, the cost will be too high. Number two, to make them habitual to use this kind of toilet, it may take years. So I don't know when your report will come about the social analysis. That will be very interesting to learn. And also, I believe you have also done some kind of the analysis investigation on the manufacturer, local manufacturer, and if they can really build the system in the local context, then what will be the cost? So do you also estimate some kind of the cost reduction of cost after this, all this after localization? Yeah.
We have set up target cost of $500 per toilet and a lifetime of 10 years. what we are doing now is not only that we are improving on the design, we are also improving on the technology so that we will actually be able to reach this target costs. We have
Yes, I
machine
had
engineers
another
working
question
on this
regarding
now.
business model and costs.
And
I
we
understand that
hope
in the
that we will
current
soon
phase
get the
you're
acceleration grant
you're
from the
also
Gates
developing in
Foundation that we
partnership
can
with
really
other
go into this
projects the treatment
re-engineering, because we need
for the
professionals
urine
in
and the
order to do
feces.
this.
And
At
first,
the
do you
moment,
have
there are too
already
many
any
parts,
indications for how
but this
feasible
is what we are
this
working on.
end product sales will
Dorothy has a
be,
question
and
there.
how to integrate this in this 1.3 resource recovery plan costs, if this can fit with the current technologies you're looking at. And also in general, what do you think about the service fee of 5 cents per person? If this is, yeah.
We think that this is feasible. We allocated a certain amount of money for the machinery in the resource recovery plant, and then we did a larger study on what these machines would cost, and we used the normal scaling cost recovery, which you are using when you are sort of making prognosis for technologies. And there were a number of technologies which could actually fit this, these cost charges. As you may know, we are doing the urine treatment, the recovery of fertilizer from urine at EARC. We are doing this routinely now in our own lab with the machinery, and we see that it's possible to get the prices down. The feces treatment is done by other RTTC grantees, and I cannot say anything about the cost there, but I'm quite convinced that we could, for instance, we could use also other technologies like anaerobic digestion, which would function really well without urine in the feces. I'm not very afraid of this part. For the logistic, we did a modeling study, and it showed that we could get down to a cost of 1 cent per person a day for logistic. And all of these prices and all of the business model we are now working on.
Yes, also to the end product sales of 2 cents. Did you
Swiss
base that on, you didn't know what product you will have actually at
set
the
up a really robust
Okay.
business model. But I'm quite confident that that can be done. And this said, I think I see one part of our toilet where we
Thank
may
you,
have
Tove.
little problems to get a fast answer to cost, and that's electrolysis. But there are so many electrolysis experts in the RTTC grant that I think that we'll get some help there. Was that answer to your question? Oh yes, we know what product will stabilize. But for urine, we only calculate it from the nutrients in urine, and there we know that we will stabilize
very constraint of space availability in India, in cities in India. We have put in sense of aesthetics into the whole module. It is compact. We have not taken much space. It occupies landscaping, putting flower pots around it. Slide. This is the first model which we have installed in the museum in Trivandrum. This is a toilet which we have installed exclusively for women users. It has a napkin incinerator and as well as a napkin vending machine. Women especially who visit hospitals. This is a school model which we have installed in around 100 schools in Kerala. Next slide, please. Coming to the RTTC project which we have undertaken, we had enabled monitoring mechanism, control system, where you can see the health of each and every toilet installed across 100. Another image of it.
Binsi? Thank you, Binsi.
That's all.
The sound wasn't
Thank you
very
very
good,
much.
but just some few questions before I give it to others. Could you tell us how the self-sterilization works? The self-washing and self-sterilization. How does it work? And two.
Okay. Yeah. It works on a sensor-based system. Like you have a sensor wherein it understands that a user has entered the toilet, and after his usage, even if he doesn't flush, the toilet after his exit, the toilet flushes all by itself. And if it's like you take that, if it's for urinating, it's less than 3 minutes, so the flushing of water will be less than 1 liter or 2 liter, whatever it is, searching on that. And if it's more than 3 minutes, the flushing of water will be less. So we have introduced that, a part of that in some of our existing toilets on a trial basis. So that is completed by the end of our grant period. And on the other self-cleaning mechanism, since we are using Indian toilets, the Indian squatting type toilet, these public toilets get muddy or gets dirty after regular usage. So after every 5 or 10 or fixed number of usages, toilet can have a floor cleaning mechanism. It has tube pipes on the corners of the floor so that pressure water flush the toilet floor.
Yeah, thank you, Binti.
Clean for the
Arno, any questions?
Well, yeah, the connection is poor, but I think the toilet is very interesting. One thing I wanted to ask you was, are these toilets actually connected to the internet, and are they continuously monitored in some way to the database on the web?
Yeah. Yeah, they have, these toilets have SIM on their, we have a back panel, electronic control panel on the back side of the toilet,
Well, that's interesting. They must be the only toilets in the whole world that have real-time functional data that are being produced. Okay, I think because of the time that's running up, we'll be going to our last speaker, Yu-Ling Cheng from the University of Toronto, Canada. Yu-Ling and her colleagues from different disciplines that are working on the unit operations approach for rapid disinfection of human waste based on the drying or smoldering of solid materials and also a sand filtration step or a
the details that other presenters have provided today. But thank you for the introduction. I also just want to acknowledge that we have collaborators from the University of Queensland in Australia, as well as the University of Western Ontario in Canada. So what Arno had said was that can you move to the next slide, please? So Arno mentioned that we use UV. We've actually modified that in phase 2 of our grant. We're now focusing on using a heat treatment process, actually identical to what to what Aaron talked about earlier. So just going through this overview process overview slide. We're not using a urine diversion toilet. It's a dry toilet. That all the human waste goes all together into the same location, and we allow for anal wash water to be used as well. And that mixed waste goes through a sand filter. We're minimizing the amount of sand that's used now, and liquid goes through one stream. Solid stays on top of the sand, and I'll talk about the solid part later, but the liquid, which we expect to have solid contaminants in that liquid filtration stream, goes into a settling tank. The liquid can then be decanted off, and we now run it through a heat exchanger with a kill tank. And it's a counter-current heat exchanger, which would minimize the amount of energy that's needed in order to heat up the liquid to the desired temperature. 65 Celsius would work for a longer period of time. The higher the temperature we go, the lower the amount of time that's needed. So the liquid we would get out at the end is a pasteurized liquid, which is free of pathogens. We're doing E. coli testing as well, same as Aaron, and which should be suitable to be used in farms or gardens. And if we wanted to get really clean water out of it, we could run it through a slow sand filtration unit, which could take longer period of time rather than just having it pasteurized in one day. But there are other processes that we can use as well to try to capture valuable things out of that liquid, possibly microbial fuel cells for getting electricity out of it, or struvite collection using some of the processes that Tove and others at EOWOC have developed. But that, we think of that as a plug-in module sometime in the future. We're not developing that ourselves. We would also then collect the solid sediment from the settling tank. We have devised a nice, clever U-tube connection at the bottom of the settling tank, where the solids would collect, and all we have to do is remove that without having to contact the solid sludge at all. Back to the sand filtration unit, the sand and feces that stays on top of the sand is then sent over, is essentially augured over into we now have a one vessel device. It is augured into this vessel, which serves as both a mixer, dryer, and eventually a smoldering reactor. So the sand and feces is mixed with residual sand from the previous smoldering process in the same unit. The residual heat from the sand, because of the smoldering process, is used to dry the sand, so to dry the feces, and then we ignite the mixture and smoldering takes place. The smoldering process can be controlled, the rate at which the smoldering takes place can be controlled by varying the airflow rate. And what we get out at the end is a sterilized sand and some residual ash from the human waste. So we've been working a lot on the energy management of this overall process. We're taking the heat in the exhaust from the drying and smoldering process and using that. So we're producing exhaust, which is hot, is also saturated with water, and we take that and use that. We condense the water vapor in that exhaust and use that to provide the heat needed for the heat exchanger. Again, similar to what Aaron talked about, but instead of using a biogas as a heat source, we're using the exhaust from the smoldering and drying process. Sorry?
Is that pyrolysis?
So, no.
Is that what pyrolysis is?
It's not pyrolysis. I mean, if you go on to the next slide. So this is just a picture of a reactor that we've been running. So if this event was happening 2 weeks later, I would have a picture of a fully integrated prototype to show you, but we're just a little bit ahead of our schedule at this point. This is a reactor we've been running in our lab. And the picture on the right, what you see is just a spoon. And what you see on the left side is what the mixture of feces and sand would look like. So that's what's in the reactor at the beginning of a smoldering process. And the smoldering front, so smoldering is just a combustion process, okay? And but the combustion takes place at the surface of the fuel, of the solid fuel, rather than the gas phase. So we don't have an open flame. The temperatures are also lower than combustion, than open flame reactions. So the smoldering front would move up through the column, and as it does so, the temperature profile in the column also changes. The temperature at the smoldering front is where you have the highest temperature. Ahead or above the smoldering front, the temperature also starting to heat up, and we get some pyrolysis of the fuel at that because of the higher temperatures that's already being reached. But if you see that the black mixture in the middle of the spoon there, that's what the fuel looks like at the combustion, at the smoldering front and the pyrolysis zone ahead of the smoldering front. At the end of the reaction, what we end up with is clean sand, which is shown at the right tip of the spoon. Okay, so if you look at that spoon and turn it vertically, okay, turn it up, turn it 90 degrees clockwise. Okay. The top of the column will have the fuel and the sand. The middle of the column, where the smoldering front is, would have that black material, and the bottom of the sand, after the smoldering front has moved through, you end up with a clean sand. Okay. Right. So if we move on to the next slide. So the liquid stream process I described before. Essentially, this is essentially what it looks like. Very similar to what Aaron described in their project before. We're not using gravity drain completely. In that we do have a pump, but it doesn't need to be a very high power pump, and all the heat is being provided from the smoldering and drying exhaust. The amount of liquid matters quite a bit. Okay, so the more liquid we have, the more heat is needed to pasteurize it. And maybe Aaron, you and I may be able to compare notes later. So we're working on a 10-person scale process, so assuming a single family scale, and assuming urine output from the family, as well as anal wash water. And we've done studies in Bangladesh to determine the amount of water that people use for anal wash, for personal wash, and for 10 people, the amount of urine plus the wash water, we started the process this year assuming that we're going to need 55 liters. We're going to have to process 55 liters a day. And that's actually quite a lot in terms of the heat requirement. And so we've worked now to introduce hoses, and hoses with aerators as well. And with hoses and with aerators on the hoses and nozzles on the hoses, the amount of water that people use has been reduced by a lot. And we've tested this with over 100 people. And so now we're very comfortable thinking that we only need to process about 30 liters of water a day. And we can provide all the energy we need from, as I said, smoldering and drying for that amount of water. And next slide, please. And this is just a drawing of what the overall toilet might look like, which we will have to show at the toilet fair in March. And just as Aaron said before, we do need for this to be elevated because everything is dropping. Well, the reason for the sand is that for the smoldering process, so think of smoldering as something like a barbecue, okay, or a cigarette is a smoldering. A burning cigarette is a smoldering process. So we have to get air to the surface of the solid fuel. And if we only use feces as a soft material, it would compress, and air would not contact the fuel very well. So by mixing it with sand, then the sand, the harder structure of the sand, the harder consistency of the sand provides a porous structure in the bed, which allows air to get through. And then we take advantage of the sand as our filtration medium as well. And so, okay.
Thank you. I have a question with regard to nitrogen. Have you been looking at the fate of nitrogen in that heated process? Kill tank.
We have not done that yet. Okay, so we are right now mainly just focused on getting enough energy there so that we can pasteurize it.
Yes,
Any other questions before we?
I have a clarification question. Did you say that you had 30 liters of liquids in total, or as cleansing water?
In total. In total.
In total.
Right.
So actually you get people down to using only 2 liters of anal cleansing water per day.
Yeah, and we're actually being relatively conservative. So we have data to support the amount of water that people use for cleansing.
Yeah. That's very nice, because we are counting on 2.5, and we'll compare notes when you see each other on how we do this.
I'll send you a slide once we get off this.
Yeah, because we are just using a normal shower at the moment, but it would be very interesting if you could send us some ideas how we can do that.
Okay.
And
Okay.
Quick question to Yu-Ling and Aaron, because both of you have indicated that you would like to have the toilet on a raised platform. So from being a toilet manufacturer point of view, do you envisage that at any point of time you would be able to make your unit underground, or at least on something which is manageable on ground? Have you ever thought about, is it there in your timeline, or this is something which you think will be evolving?
I guess I can go first. So lowering our toilet is something that we would like to do. The complication for us is because everything is totally gravity fed, and we want our heating system to be above ground to avoid any complications with flooding or the flame going out. We want the heating system to be accessible. So we're looking into ways that maybe we can lower it. If we can maybe create some sort of system where everything can be totally underground but still accessible or flood-proof, that'd be ideal. And so we're working towards that. But for the first pilot study, we wanted to make sure to avoid as many complications as we could. So that way we made sure that the toilet was lifted above the system and everything would operate by gravity flow.
We think about exactly the same things.
Thank you.
We think about exactly.
Okay, thank you. Okay. We're glad to hear that.
The thing about
Being on the
above
other end.
ground toilets are that they are flood-proof. They can actually be more resilient in high water situations. It could actually be useful from that point of view. Any other questions? Otherwise, I think we're going to tie it up for this session. We've heard about effective sewage sanitation with low CO2 footprint, the on-site ultrafiltration water recovery, the portable automated self-sustained toilet, and the rapid disinfection of human waste.
What is common in all four projects that we listen to is attempts to create self-sustained innovative designs and systems, whether they collect urine and feces separately or together. Aaron and Yu-Ling have presented systems that generate energy that is in turn used in the system. Tove has presented a system that recovers, treats and recirculates water within the system. And Binsi is presenting a system that actually generates money through advertisement. So this actually demonstrates that with some creativity in ways of thinking, ways of design and ways of working, one can actually design the toilet to serve different purposes. But however, what remains the next challenge, which is the big one, with all these systems that we've listened to today, is the feasibility of their implementation in large scale, especially in those contexts that you are testing them. Not so, Arno?
Good. Yeah, so on behalf of Stockholm Environment Institute and the Sustainable Sanitation Alliance, we'd like to thank you for joining us to share this very interesting session about these innovative projects. And we'd like to wish you all good luck, each of you that have participated here in your further field testing. We also look forward to discussing your projects further with you on the discussion forum. You can see on the lower left the the address for the website for this is a discussion forum. And without any further delay, then I would like to thank you all for this late night meeting we've had. To Binsi, who had stayed up late in India for this, and for Aaron, I guess it's just the morning for you. So, as well as